Okay, so I'll try and not knock this down. Apologies for the random setup on an iPad, but as the best I could do at home. So we're going to have a quick recap on Chapter 8. I just wanted to go over three things with you, really. One was the energy density stuff that we did. One was black body radiation, and the two kind of laws that went with that. So this is kind of Chapter 8. Now, we haven't done this lesson yet, but we're going to go into solar radiation on Monday. And in there, we talk about something called albedo, which I think is how you pronounce it, but also the solar constant, and that ties in quite nicely with what we've previously done. So I will go into that, but obviously be aware if you watch this before I teach you, we haven't done it yet. So far, when you've been growing up, we've talked about kind of three different ways of measuring energy. We've talked about energy, and we've talked about, two different ways. We've talked about energy and we've talked about power. And occasionally we've talked about something called specific heat. And obviously when you got to IB, you also looked at latent heat. So that was the idea that if specific heat was the amount of energy required to change 1 kilo by 1 degree, specific latent heat was that idea of being able to change state. Now, there are a couple of other things that work better when we're talking about fuels, and those are specific energy and energy density. So one of them has the symbol ES, and one of them has the symbol ED. Now, I remember it as when you were doing specific heat, this was the energy required to heat up a kilogram by 1 degree. So if this is the amount of energy required to heat up a kilogram by 1 degree, then specific energy is the energy per mass. So it's the energy per kilogram. And so I think that one is probably the one that fits most logically. Energy density, on the other hand, is slightly different. Okay, and energy density, rather than being the amount of energy, I can't spell, rather than being the energy per mass, energy density is energy per volume. And the way I would probably remember that is that whenever you're doing anything with density, we have to know the volume. So for me, I would sort of think, oh, okay, density, it must be per volume. Specific energy sounds like specific heat, so it's the energy per mass. And they're related by one another. So if this is, if this is joules per kilogram, and this is joules per meter cubed, well, you may be able to see that I've got joules here and I've got joules here. So they're very, very similar to one another. I've also got kilograms here and I've got per meter cubed here. So there's a couple of terms that we've seen before. So if I do energy density, so if I do joules per meter cubed divided by specific energy, so I divide that through by joules per kilogram, then to divide it through, it flips over, so we end up with joules per meter cubed divided through by joules per kilogram. This flips up the other way, and then the joules cancel, and we end up with kilograms per meters cubed, which many of you will remember is our formula for density. Now again, you don't need to do anything with that, you don't need to do a huge amount of maths with it, but you do need to realise that all of these three things are tied together, and being able to sort of understand that is quite important. We looked at an example question in that first lesson, which was use the values for specific energy and the energy density to calculate the density of a particular material. And there were a couple of things that you need to know. One was it was in megajoules, so there's a little bit of conversion there. But generally speaking, this is kind of learn the definitions and make sure that you'd be happy doing sort of joules per mass or kind of a joules in volume. Now, I'm not going to go over the power station stuff because a lot of that was to go away and learn it. But I think the thing that we perhaps spent quite a lot of time on last lesson was this idea of a black body. Now remember, a black body is made up. Oh, sorry. A black body is a way of representing something that absorbs all of the radiation that is incident on it. Okay, so something that takes in all of the radiation that is incident on it and does not reflect or transmit any. Since a good absorber is also a good since a good absorber is also a good emitter, a perfect black body would also be a fantastic emitter of radiation. So if we were to look at a perfect black body, we should see emission of light in every single part of the spectrum. Now, like I said, there aren't any perfect black bodies, but stars are a pretty good way of looking at them. And so if I was to start with one thing, it would be go away and learn that definition, the one that's in our OneNote. The second thing I would understand is, well, how are light and energy and all temperature and all those kinds of things related to one another? And that came back to the formula that we looked at, which said E is equal to HF, which is also the same as E is equal to He over lambda. These are both formulas. They're the photon formula that we used in chapter 1 of physics. But essentially what they say is that energy is proportional to 1 over wavelength. Now the reason why that's important, and he says looking for another pen, hoping that this one is slightly better. The reason why that's important is because a short wavelength means high energy, and a longer wavelength means low energy. And some examples of that are, if you imagine the electromagnetic spectrum, we have things like radio waves, infrared. These are all long wavelength light. Okay, these are all long wavelengths. Whereas X-rays and gamma rays are high frequency or shorter wavelength, and therefore they have more energy. Now, for for visible light, we have the colours of the rainbow: Richard of York, cave, battle in vain. And so red light is our longest wavelength, so this is low energy. And violet is our shortest wavelength, so this is high energy. So when we're looking at stars, we can determine their temperature by looking at the peak in light that we see. And so for our own sun, because our sun looks orange-yellow, it falls somewhere in this end of the spectrum. So it's a hot star, but it's certainly not the hottest star ever. We see stars that are in the blue and the indigo section. Now, if that light falls onto our Earth, we're able to analyse it. And we're able to analyse it using Wien's law, which is spelled W-I-E-N-S, Wien's displacement law. But before we do that, I'm just going to come back to this here. And this is the graph that we plotted, and that was intensity versus wavelength. And what we talked about in the lesson was, well, okay, if I looked at the wavelength of light given out by a star, what does this look like? Well, for a really cool star, we get this spectrum, we get this range of light with a peak, lambda max. And if we look at something that's slightly hotter, we end up with the same shape. It's the curve. Sorry, I've actually drawn that incorrectly. I'll try and draw it in red to make it clear. It looks like that, so please ignore this. So they follow a similar pattern here. We've still got them both going down. As that wavelength increases, the intensity of light decreases, which makes sense. But what we see with a hotter star is the peak wavelength, the light that we see most commonly is towards this shorter wavelength, because remember, shorter wavelength, high energy. It's a narrower peak. This one is broader, this one is narrower. So this one here, much narrower, much broader peak. This one here is much narrower. And again, if you had a really super hot star, be narrow, and then it would fall off. So this peak in wavelength is what gives the star its colour. So for our own sun, it looks to be yellowy orange. And so we find that our peak is about 6,000 Kelvin. Something that's slightly cooler down here might be something like 2,000 Kelvin. And I suppose the next question is, well, how do I know that this is 6,000 Kelvin? Well, that comes from Wien's law. And Wien's law related the peak wavelength that you see and temperature. So what he said was that, well, the peak wavelength you see multiplied by the temperature equals this constant. And so what this allowed us to do was to look at light from different stars, look at the wavelength of light that it was giving out, and then predict the temperature. Now, you may remember this from thermal, but temperature is just a measure of energy. That's all it is. Temperature measures the average kinetic energy of the particles. That's all it does. The average kinetic energy of the particles in a system. So if you've got a really, really hot system, that makes sense. You've got the particles moving around a lot faster, they have a higher temperature. Well, anywhere where you've got energy, you can also talk about power, because energy is kind of absolute, that's total value, whereas power is kind of rate of energy transfer. So if I've got a really powerful athlete, they will give out their energy much, much quicker. Think sprinters, Olympic weightlifters, gymnasts, whereas a marathon runner, sort of low power. And this leads into Boltzmann's law. And so these are kind of our two big equations here. And so we have that power is equal to this symbol that we've not looked at before, multiplied by A, multiplied by T to the 4. So we've got temperature, we've got area, and we've got a constant. Data booklet. Don't need to know anything about it, just need to be able to use it. But what this tells us is that the power of a star, or the amount of energy being given out by a star, is proportional to kind of two things. It's proportional to its area, and it's proportional to its temperature to the power of 4. We're not going to derive where this comes from, but it's important to realise that if I have a hotter temperature, I have more power. If I have a bigger area, more power. But the challenge here is that every area that we often look at is pi r squared. Well, actually, in reality, we're talking about a star here. So if we're talking about a star, we need to think about the surface area. Okay, so we're trying to find the surface area. And therefore, if we're trying to do the surface area of a sphere, we've got 4/3 pi r cubed. He says, wanting to check that. Four pi r squared. It's the volume. 4 pi r squared. And so, very, very similar. This would just be the area of a circle, whereas this is the surface area for an entire sphere, and that allows us to do some calculations off the back of that. So we're going to look at a question like this in Monday's lesson. So revisit this, okay? Think about a couple of things, like if I'm comparing the power of two objects, how does their size compare and how does their temperature compare? Because you could have something that's very, 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 very hot, but very, very small, and therefore the amount of energy that we receive per second is quite low. And so that'll allow us to do it. Now, moving on finally,